Okay, good morning again, and thank you for joining. We'll start the class. I'll share my slides with you. Okay, so in the last class, we defined two categories of agents. One which is standardized environment, and then the other is the real world problems. So standardization of the problems and the real world problems. And one of the standardizations that we discussed was that of the grid world problem. So just looking at it again, grid world problem. So like, for instance, if the start state of this moving tile puzzle has been shown, an example of a started state has been shown here, and a goal state has been shown, where you have to arrange these tiles in the order of the numbers. So just to have an estimate, how many different states are possible for this particular moving tile problem? We discussed this last time, but just to recall it. So how many different states can be defined for this 3x3 moving tile puzzle? Can anybody give me an estimate?
9 into 8 factorial, I think.
9 into 8 factorial, is that enough, or you have to do more?
Because the this bang tile could be placed in any one of the 9 positions. So there are 9 possibilities, and once it is fixed, we need an arrangement of all these theaters, which we can do by 8 factorial.
Excellent. Yes. So 9 into 8 factorial is the number. You can imagine that this number is huge, right? So even a very simple problem of 3x3 grid requires, if you want to solve it exhaustively and try all combinations, it will require a very large number of routes, how we go from this start state to this goal state. In theory, the complexity of this problem is to search for all the trajectories from the start state to goal state. And now the number of nodes we know, like the number of stopping points in a navigation system. So you have n into n factorial, roughly order of magnitude is n factorial. So n factorial number of states. And how many edges would be possible now if you have to draw a path through these states, and if each state were to be represented by a dot in a graph? So how many paths can be created from a start state to goal state?
Can you, I didn't get the question.
So now what we worked out just now is n into n factorial, which is the number of states available to you. Now your initial state may be anything, like in this example, you have an initial state called start state here, and you want to reach to the state which is shown on the right. Now only some moves will be allowed. Let us say the motion of only one action is allowed for the blank tile. So if I have to trace all the possible paths from my current state to the goal state, will it be more than the number of states or less? Or can you give me an estimate of that number as well? So you can think of this now, a graph where the number of nodes is already computed, n into n factorial, or order of magnitude is n factorial. And through the n factorial nodes, how many different paths are possible? You may be at any given location, and the goal state may be any state amongst them. So how many ways you can traverse from the start state to the goal state? So the problem for an intelligent agent would be to find that route from the current state to the goal state, which requires minimum number of states, minimum number of steps, or which has the minimum action cost. So if every step, every move requires the action cost is 1, so you have to calculate the path which requires minimum number of edges to travel, which is called in the graph the shortest path. Now there are two situations. If the graph is completely connected, how many steps are required to go from the start state to the goal state? This is something about graphs. Have you read about graphs in networks in any other course?
Is discrete mathematics.
Yeah, so maybe you already know more than me in this case. So can I ask you this simple question? If a graph is completely connected, how can you compute the number, the shortest path from a given initial state to a defined goal state?
By following a greedy algorithm in which for the start node we see which edge has the least action cost, and like that we keep.
Let us say all edges have an equal action cost. I think the answer is simpler than that. It's just a little trick here. You're missing the word. I'm saying graph is completely connected. That means every node is connected to every other node. If every node is connected to every other node,
we can directly go to it.
You can directly go. You just need one action cost is one. So you just need one single step to go there. But if it is, the problem arises when it is not completely connected. So if you have to play this game of a moving tile puzzle, you think it will be completely connected?
No, in this case, no.
It will not be completely connected. So how typically can you guess to a given node, how many connections would exist to the nearest nodes? So in other words,
right, because if we move, we have to write or up and down.
Yes. So to every random node or any random state in this grid world problem, the number of connectivities will be defined as the number of allowed moves. So if there are 2 allowed moves, or there are 4 allowed moves, or 6 allowed moves, whatever is the number of allowed moves, that will determine the number of nodes which are connected to the start state. So nodes and state I'm using equivalently now, because every node on the graph is representing grid state. So when we deal with a grid world problem, the number of tiles in this grid is not the size of the complexity. It is actually the number of ways in which this grid can be arranged. So I'll take some examples. I took last time some examples from this real world examples where this grid world problem has been considered. So some of the examples are route finding problems and their extended version. So route finding can be thought of at every traffic signal is considered to be a node, and then how we go from one node to the other node in order to navigate to the final goal destination. So airline travel problems, so they have to define, suppose now airline has to, okay, let me not explain it. Let me allow you to formulate this. How will you formulate airline travel problem as a grid world problem?
By airline travel, what do you mean? Between 2 destinations?
Just try to work out. So suppose you are running an airline travel company or airline company. Now, how would be you? What do you have? What is a typical task you will have? You will have multiple destinations, and you want to have minimum number of flights so that maximum number of destinations can be covered. You understand? So you don't want to have the plane going every pairwise. You cannot have that many number of planes, right? If as an airline company, if your airlines is touching say 1,000 destinations, you cannot have 1,000 planes. You will have fewer planes. So what will happen? How will the planes will be utilized? They will go from one destination to the second destination, and then further to third destination and fourth destination, and perhaps back. So that is how they will go. The different planes will be utilized. So very small number of aircrafts will be sufficient to cover all the destinations. If, of course, they will not be used at the same time. So can you formulate this broadly speaking as a grid world problem?
Yeah, it would require the arrangement of the destinations in a grid, according to which one would be visited first.
Okay. So let's say I have 5 destinations and I have 2 aircrafts. So can you make this? You will have to consider the action costs such as distance. And why other people are not participating? Only one person is participating. Other people, please join the discussion. So if in this grid, if I represent every tile-like problem as a kind of a destination, and then how do we move the aircrafts from there? How can we find?
We can model the blank spaces in the tie as the aircrafts that are available and the numbers as the destination.
Yes. So how will you define the initial state?
The initial state would be both the empty tiles at the first and second location, and then.
So let us say I have 9 aircrafts, and I have 9 destinations and 4 aircrafts. So what will be your first formulation of the grid?
We have 9 destinations, right?
Yeah.
So the 9 destinations are arranged one by one, one after the one in the grid. And before that, there are 4 aircrafts, the blank tiles that are there.
So I can make, for convenience, I can make it as a 3x3 square grid just to make it 2-dimensional. Although I'm not ensuring that any two elements of this grid are connected to each other physically, but just for arranging purpose, I arranged 9 as a 3x3 grid. So it looks like a grid world that we just saw. And how will you show the aircrafts now? How many initial states are possible? You have 4 aircrafts and 9 destinations. You start from somewhere. So how will you start?
9C4, you choose.
9C4 combinations. That means these 9 positions can be occupied by any of these 4.
Yes.
So for each of these 4 aircrafts, they can be placed on any of these 9 positions. So will it be 9C4?
Out of the 9 destinations, we choose 4 to which our aircraft should fly first.
That is where you're assuming that they cannot be exclusive. At one destination, 2 aircrafts cannot be present. Is that the assumption?
Yeah, I am assuming that all 4 aircrafts are at the True.
So you're at different locations. So again, you have to define the boundary conditions. So if the boundary condition is that each aircraft has to be at a different location, 9C4 is the total number of initial states. One of them will be at the goal state. So, but in this case, there's a goal state is to have the maximum number of destinations covered over a period of time. So that will be now the grid will have to be incorporated. The grid has to incorporate the destinations over a period of time, say after 10 flights or 20 flights. So grid will become larger. Time factor will also be considered here. But at a given time, you can say that how the graph is moving from one state to the other. And if my problem is defined that I want the aircrafts to move around between different destinations so that the maximum number of destinations are covered. Or the
number.
Yeah.
So the number of possible start states would be 9C1 plus 9C2 plus 9C3. And no, it won't be 9. Yeah, it could be 9C3 or plus 9C4 because either the aircrafts could be at one position out of the 9, they could be in 2 positions, or they could be in 3 or 4 positions.
Yes.
Assuming that they are identical and their arrangement we are not taking into account which aircraft is.
Excellent. So of course, when the real world problem comes, you may have to define further the aircrafts are smaller or larger, and it becomes more complicated. But in the simplest form, you're right that since I'm allowing multiple aircrafts to be in the same destination, so there will be 9C1 plus 9C2 or summation of 9CI, where I goes to 1 to 4. That number will be the number of possible states at a given time. And then how does the how does the action change this graph? What are the states which are available? So now grid is one thing, state is another thing. Grid nodes in the grid are not representing state. The state is represented by the arrangement within this grid. So at any given instant of time, and let us say I don't allow 2 aircrafts at the same destination to avoid this series of the combination problem. I just use 9C4. 9C4 is the total number of total number of states, initial or final, whatever. 9C4 is the total number of states when when one aircraft can be only at one location. Not more than one aircrafts are at one location at a given time. So total number of accessible states to the system or to the agent are 9C4. And how do you determine the best possible itineraries now? You have to determine different itineraries, how they should be scheduled so that the maximum number of destinations are covered with minimum amount of cost. So you have to define an action and the cost model here. What will be the cost model?
The aircraft should fly to the nearest destinations, which of them?
Yeah, so the distance or fuel consumed, or maybe the airport taxes, whatever you say, there will be, you have to define for each individual aircraft, you can define the cost of its cost going from one grid location to another grid location. That cost, which is defined at in single aircraft level, will have to be converted to the total state cost, state to state transition cost. So if only one aircraft is moving, then cost will come only from the movement of that aircraft. If two aircrafts are moving, then the cost will be accordingly added. So now you can fix a goal. Your goal is to cover maximum number of destinations in a matter of 1 week or 2 weeks or out after 100 flights. So this way you can fix the goal. And then you will start searching the routes within the space, state space, not on the grid. So state space will have to be traversed. And the state space, how many different combinations are possible will become infinite actually, because you can come to and fro, and you can go in any different directions. You can go multiple times if that is allowed. We can have really a very large number of trajectories, and you have to choose from them one trajectory, which is the best. And again, some of the trajectories may not be allowed, some of the trajectories may be allowed. So all those factors will be considered, that how can you move within the state space. So which states are connected, which states are not connected. And with each connection between state, what is the cost model? Based on that, so at this point, I'm not defining this problem in the entirety. What I'm trying to say is giving you a kind of a feel how this grid world problem can be utilized as modeling the airline travel problem and trying to optimize the number of flights required to cover the maximum destinations. And another example that is written here is the video streaming over a network, P2P streaming. You know about P2P streaming, right? How it works. Can somebody tell me how P2P streaming works? And how it can be treated as a grid world problem? You can guess it even if you don't know.
It's peer-to-peer, so one peer sends it to the another one, and then another one sends to another one. Yeah, exactly.
Yeah, so many of the streaming services work like this, that you stream, suppose the IPL matches are being streamed on one server. And now every user of that app, they receive that streaming. And now to the other users, the streaming is not done from the main server. The streaming can be done from the server, from the user or peer, the client who is using the original streaming. So that way they can save the bandwidth of the top server. So now this can be formulated. What is the best way from which particular, if they at one time, suppose 100 users are connected to the network and they're watching IPL. So what is the best destination for me to watch or for an individual user to watch? So there are many different combinations are possible. And these combinations can all be represented as a kind of a grid world problem. So all users who are watching or who are connected to the app at a given time, they form like a grid. And the goal of solving this grid world problem will be, in this case, how to go from the initial state when the X number of users currently have the streaming receiving, and then the goal state is that all users should be able to receive the stream. So what is the best route to reach there? And there will be what is the action cost. So action cost may be determined in terms of the bandwidth that every user has, in terms of the number of other users that are already connected to it, etc., etc. Taking all those into account, this also can be formulated as a grid world problem. Very similar problem is also a problem called traveling salesman problem. This is also to some extent already a standardized problem, traveling salesman problem, because many other real problems where actually the salesman is not involved are also solved in the manner of traveling salesman. So let's have a look at what is traveling salesman problem. Have you heard of this?
Yes, sir.
Yeah.
No, sir.
So even if you've not heard, you can guess it. So how will you formulate it? So I'll ask Aditya to keep quiet for some time so that others can participate. Please, other people should participate. So it should not look like just a conversation between Aditya and me. I'll call you by names if you can't, if you're not volunteering.
It's like a problem in which the salesman travels from one city to another, and he has to cover all the cities at the minimum and cover the minimum distance.
Okay. Yeah, so you know this problem. So can you think of organizing this problem as a grid world problem? First, you will define your grid to be delivered or not delivered, or traversed or not traversed at a given time. So what will be state at a given time? In the grid, every it is similar to the tile problem that we showed. So every tile can be thought of now a destination. And what is the initial state here? How many initial states are possible? Let us say there are 100 destination, 10 by 10 is a grid that we are forming, and there are 100 destinations to cover. So first of all, how many states are possible here? That's not so difficult. I have a 10 by 10 grid, and there is one salesman that can be at any given one destination at a time. So there are just 100 states now. Each destination is a state. Is that right? So there are 100 states in this way. And what is the out of these 100 is that means it is you have a problem, something like there are 100 nodes, and in which a salesman has to go from one node to this. What are the possible actions? What is the action space? So let me formulate it broadly speaking. So you will have to have three pieces of information: where the salesman is currently located, what are the destinations which have already been covered, and by default it will also give you the destinations to be covered now. And the goal state is when all the destinations have been covered. That is your goal state. So, and salesman can be anywhere, that doesn't matter. So starting from an initial position where you know that suppose state 1 and state 2 has been covered, the grid positions 1 and 2 are covered, and there are additional 98 states to be covered. So this is your initial state maybe. And then actions, possible actions are going from 2 states covered to 3 states covered. And the action cost will be maybe the distance to the destination, which is now being included. So the combinations that you have to try at every location is what is the next grid. So suppose 2 grids have been covered. What is the third grid to be added? And every grid that you are adding will have a different action cost. So in the end, for every trajectory to go and cover all of them, so you can think of it now as the total cost required, and performance can be measured accordingly. So these are additional problems which have been shown here, and I'll take some example from biological systems, so you can have this feel of how such intricate problems of biology are also being solved using these theoretic concepts. So there is, for example, a question of protein design as an assembly problem. So what happens in this, if you are interested in reading the entire algorithm, you can access this paper from Cell Press, which was published 2 years ago. So they applied the deep graph neural networks to solve the protein design problem. Has anybody heard of what is a protein design problem?
I have a very vague notion of it.
Yeah, vague is fine. So, okay. Yeah, please go ahead.
From the fundamental 20 or so amino acids, we try to design a protein that we have, so that we want, that we can use for some I do not get the exact biology of why we do it.
Yeah, okay. So since protein performs some function, or you may be designing protein to have a particular structure or to have a particular function. Let us say a structure. And the structure is dependent on what is the sequence of the amino acids you place. So suppose a problem can be roughly defined. So your answer is correct. So I'm just elaborating it. So suppose I want to create a sequence of amino acids. Now there are 20 amino acids possible. So I'm creating a sequence of 20 alphabet letter, 20 alphabet language. And then using the 20 letter alphabet, I'm trying to create a sequence of a given size. It may be a fixed size, it may be a variable size. Let us say I create a fixed size of 100 letter word. That means 100 residue or amino acid residues. So I want to find that sequence of 100 residues that gives me the best structure or desired structure that I want. And that desired structure there may be some method, some algorithm that converts the sequence into a structure. That may be another program that can do that for us. So let us say I know the program, I give the sequence, and I will be able to calculate the structure. So now in order to find the right structure, because I cannot go in the reverse order. I cannot say this is my structure and these are the kind of amino acid sequences that will be produced that will produce this structure. So there are methods to convert sequence into the function or into the structure, but no reverse method. So reverse method has to be by designing different possibilities and then predicting what is the structure and matching with the desired goal state and seeing, okay, now my goal has been fulfilled. So now in order to try this randomly and try to do exhaustive combinations, what do you think? How many combinations are required here?
What is the chain length that we desire?
So 100, if chain length I want is 100, and the amino acid alphabet is made of 20 letters. So it is, you can simply compute what are the different combinations I can have.
20 raised to 100.
20 raised to the power 100, because each position can be occupied by any of these 20 amino acids. So 20 to the power 100 is the number that I have to try. And if even if I have a very fast algorithm that can convert the sequence into the structure prediction, it is a huge problem, and it will take really a long time to solve this problem. So that is why the intelligent method is required for this. So the method that can be utilized again is the grid search problem can be utilized here. And how can I use the grid search problem in this way? That I define this now 100 residue length sequence is like my grid. And in this grid, I will place the amino acids which are there currently. And then how many states can I define?
Initial states.
Yeah, any number. So any state can be an initial state. So you define one of them. You start anyone. So it's the same number that we just computed. 20 to the power 100 states are possible. right? So each of the protein assembly or the sequence that you have is a kind of a state. Although the grid size is 100, but the number of states accessible are 20 to the power 100. So now I want to change now. How will I reach the goal? Is like, I think I can assume that this is my state, and I can keep on changing one amino acid at a time. And I go from one state to the other. I can change one amino acid, so I will get a new sequence or new state. And I can check whether I'm getting closer to my destination or I'm going away from my destination. So my new structure is closer to the structure I desired or less. If I'm getting closer, I will find some method to find the optimum goal state, that is to match.
Sir,
Yeah. Yes.
so 20 to the power 100 is the number of sequence of all possible sequences. Then how you are saying that 20 to the power 100 will be the initial state?
No, initial state will be just one. I'm saying 20 to the power 100 are the total number of states accessible to you.
Okay.
Initial state will be just one of them. It can be any random state from here. That is your initial state. Right? You understand? You agree?
Yeah, yes.
Okay, great. So now one way will be I keep on trying random number of combinations. So exhaustive number will be 20 to the power 100. No computer can do that number of calculations in a realistic time. Even an assembly of 100 residue amino protein will be almost prohibitively large. So what we do is we start from any initial state. And any initial state means I randomly assign any of the 20 amino acids to these 100 positions. And then I go incrementally by changing one amino acid at a time. So I replace one amino acid by another amino acid. So if I go change one amino acid at a time, how many actions are possible? For every state,
20.
20 actions are possible. That means every state is connected to 20 other states. So I can go to 20 states and then 20 next state to corresponding to each one of them. And that is how I can gradually expand. And my goal again is I have to find the best method so that I can reach the goal state with minimum number of steps required or minimum amount of action cost. Action cost in this case, one amino acid changing, or we call it mutation, one mutation at a time, is kind of a cost for you, action cost. Or can we use a unit cost model can be utilized in this case. And then so what is the cost? Design problem here is how long it takes me to find out the best sequence that will give me the structure that I desire. So this is again, very easily we can think of it as a grid search problem. So this is another problem you can again look at. So I'm citing some of the recent papers which have appeared into the method that people have reported in 2019. The last one I showed was 2020. So during last 2-3 years, these papers have started coming in top journals. So PNAS is one of the top journals in the field. And the last one I showed was Cell Report. So these are top journals which gives you an idea of how important are these problems to be solved, and they still are not completely solved. How can we so if you may have heard of AlphaFold, where structure prediction is carried out, that is another problem, but that's not being formulated as a grid world problem. So these are some of the problems that can be formulated as grid world problems. Okay, so this is the detail of how we do the protein folding process. The protein folding process is if I have the protein sequence, amino acid sequence, which is given to you, then what happens actually is that every protein sequence, amino acid sequence, ultimately folds and takes some structure. So when it takes some structure, it passes through certain transition states, and then it goes to this final structure, which is called the native structure. So now this trajectory of going from one state to the other can be thought of each individual node changing its position, and the early folding residues show the connectivities. Initially, maybe all of them are unconnected. That means this residue, all of them are at a long distance. But as it starts folding, some of the residue pairs start coming closer, and some of them remain away. So those which start coming closer, they are connected by an edge, and those are still away, they are outside the they don't have the direct connectivity. So they may early folding residue may be seen like this, that they have got connected to two. They have connected to two of them. So then there are functional residues, maybe another aspect of it, which may not be maybe not needed for this immediately, but that is
What do you mean when you say residue?
So yeah, so residue is actually the term for amino acid when it is part of the protein. So when amino acid is free, we call it amino acid, but when it becomes a part of the chain, it is called a residue. It is called residue because one of the hydrogen and OH group has been removed, and it is not an entire amino acid there. So it is sometimes called amino acid residue or simply a residue.
And what is a functional residue?
So functional residue is another level where these some of the amino acid sequences they participate in some function. Maybe they are binding to DNA, or maybe their drug is binding, or maybe they are hydrolyzing an enzyme. So that doesn't happen at the whole protein level. That happens at local sites, which are defined at the level of amino acid residue. So the sites where these functions actually take place are called the participating residues are called functional residues. Okay. So this problem of protein folding, again, now the goal is computational definition of the problem is that you are given a sequence. Can you tell what will be the final folding structure? What you know is the forces between the atoms and the forces between the residues. The forces are defined in terms of some what is called force field. Suppose you know the forces, you know the energy that will be released when they come closer. So what are the different, what is the final possible structure? It's a very complicated problem that people have been trying for a long time. Recently, there is an AlphaFold that has been solved by Google by its deep neural network. So that is now a very famous story that AlphaFold was solved. So what has it solved? What it has solved is that given a sequence, it can tell you what will be the final structure. And as a grid world problem, what you have to think of this is again the possibility as at which of these two residues are connected and which are not connected. And as the folding continues from the start, when it is in the extended or stretched out state, and when some of the residues start coming close to each other, so we say they have folded. So like this dotted edge, this is still in the formation of an edge. In the next stage, this will become an edge. So more and more connections start happening. And therefore, in the end, you will have this native-like structure. So the goal of the computational goal will be, given the forces, given the nodes, can you find the optimum state in a realistic time? So the classical method is to do a molecular dynamics so that the proteins can be, and the Newton's laws of motion can be applied, and the forces can be computed using simple equations of such as what are the force electrostatic interactions, the covalent interactions, etc. So the forces can be defined between each atom. And if you know that this is the current state, then I can calculate the force on every atom. And then I can say, I can let the atom move for 1 millisecond or 1 picosecond or for a very small amount of time. And I can see after this, according to the equations of motion, what will be the next location of this residue or this atom after in the next step. So we do it step by step. That's such a technique is called molecular dynamics. So in molecular dynamics, you can do it, but molecular dynamics takes a long time because you have to solve the equations of motion for a large number of atoms. Each of these amino acids itself is made up of several atoms. So now many ways are being attempted to do this. For example, instead of solving the force for every atom, people try to do it for a larger chunk, which is called the coarse graining. That is, you don't solve it for each grain, you solve it or for a larger system, and then try to find approximate solutions. So the gaming theory or the graph representation theory can be applied. If I can calculate the forces on all, I do not go through the molecular dynamics method. I go from another gaming approach, the grid world kind of a problem, and try to and hope that those methods can also give me the final state. And this method has been successfully applied by Google in a solution which is called AlphaFold. So now we come to if all this time we have been discussing that I have an initial state, I have a goal state, and I want to find out what is the best route to this quickly. So we'll look at some of the algorithms which people have developed to find the fastest, the best path to go from the initial state. Now remember that you can always solve the problem of going from initial state to the goal state, or we can always solve the grid world problem or the shortest path problem by exhaustive sampling, by trying to combine all possible paths and calculating the cost of every path. The problem is not that this problem is not solvable. The problem is that all possible paths are so many. Combinatorial problem is prohibitively large, and it is not possible to solve the problem in an exhaustive manner. That's why we need to have faster algorithms. Now, these faster methods will sometimes come at the cost of, being sure that your answer will come, or being not necessarily the best answer. They will sometimes give me a suboptimal answer that is not the best answer, but maybe the answer which is doable, which is good enough for me. Maybe later on I can find even a better answer for that. But for now, since I can quickly find it out with minimum action cost, I can say my algorithm is working. So it depends on the trade-off. In some cases, I want to ensure that I should get a solution. In some cases, I'm okay with a suboptimal solution. So we'll cover some of those. So I think the whole concept has been explained in the last discussion so far. So if I can take another example here, I have initial state when I was navigating to University of Delhi from administration block. I could have used this kind of a graph representation that here from here, my current location is like my node, my state, and the locations will keep on changing from here to North Gate or East Gate, all possible states. And then I traverse a path. Instead of tracing all the paths, I find the best path from the beginning so that I can just follow it. So now here comes the concept of search tree and state space. This is the last concept of that I'll discuss today, and then we'll start looking at expanding the search tree. What does the term suggest to you? What is state space and what is search tree? This is some illustration that can give you an idea what I'm talking about. So we based on the discussion so far, I think you can figure out what is search space. What do you call it? Search tree, sorry. Yeah, I just lost that track. So search tree. Search tree, I have not used the term search tree. What I have used so far is the state space. So can you tell me what is state space?
All the possible states in which the environment can be.
Yes. So all the possible states plus one more thing. Possible connections. So that means allowed actions are also included. So it somehow tells me that I can go from this state to this state. All states are not accessible from every state. Yeah, this is an important point. So if I have the state space now, so I can think of my goal. If I want to go from initial state to the goal state, I have an entire space from which I have to find. So in this entire space, I want to find that route which can take me fastest or to the goal state. Fastest here means I have to find that route which has a minimum action cost, cumulative action cost of all the actions that I will perform in going from my initial state to the goal state. So on top of this, I'm introducing now the term search tree. So I already said that while traversing this state space, I do not traverse the entire space. I do not try all possible combinations. I want to try minimum number of steps or minimum number of actions. A good algorithm or good method will be one, so that does not let you try too many combinations, which can take me to the goal state or which can give me the path to the goal state without having calculated the action cost of every path. Theoretically speaking, if repetitions are allowed, between the initial state to the goal state, an infinite number of trajectories are possible, right? If the repetitions are allowed, you can go forward and go back and go forward, and you can have any number of combinations. But in reality, when you travel a path, when you go from any state, any location to another location, in reality, when you travel, when you decide to take a particular route to reach a destination, you do not try all combinations. You can often find out the best route without having tried every combination. So if you have to go, say, for example, from JNU to Delhi University, you can also go from JNU to Delhi University by first going to University of Mumbai, or by first going to ISC Bangalore and then come back to Delhi University. So actually the number of routes possible in this system, when the entire state space is composed of any destination in the entire country, so this state space is really large. But in order to find the best method, I don't even have to try to take the route to IISc Bangalore. I should have a way to limit my search. So the part of the state space graph that I actually travel to search whether it is a good path or not a good path, that is called the search tree. So that is I create a tree. I start from top and I branch out to 2 possible directions or 3 possible directions. And from there I branch out further. So I keep on branching out and I keep on trying this particular branch, whether it is effective or not. And this path, which is actually I am contemplating to take, which I am comparing for which I am computing the action cost, that is called the search tree. So as in this graph, you would see that the state space is made up of all these blue edges, and the red space is actually the search tree. Suppose the blue part is the state space. So all of three, stage 1, stage 2, stage 3, this state space is not changing. This is fixed. But in this state space, you start from this location. And at this location, you had 3 possibilities. You could go to the top, you could go to the right, you could go to the bottom. And after, in each of these 3 edges where you would reach, you would have next the possibility from here to go to only this location. Only 1 possibility is left here. At this location, there are 2 possibilities. At this location, 1 possibility. And this way you can expand the search tree. Now, the goal of finding the best route from the initial state to the goal state reduces to this, that I want to expand my search tree, and I want to expand my search tree in such a way that I have the maximum likelihood or maximum possibility of reaching my goal state with the minimum cost. So now I have to find different ways of expanding my search tree. How should I expand my search tree? Should I continue to, for instance, in this case, I am expanding the entire tree. Should I continue to expand this particular branch only and stop searching on this side? Or should I expand all of them first? Based on this, there are different algorithms that will be defined. So I'll cover those algorithms in the next class. But this was to explain to you.
Are they based on depth first search or breadth first search?
Yeah, exactly. That is what we will talk about. So depth first, breadth first, and what are the trade-offs. So you have already, if you have already studied them, so these will be just a repetition of that. So we'll just have a look again and how they work. Great. So anything else? So you have studied this again in discrete mathematics?
No, in algorithms course.
Algorithms course. So those will repeat here. Perhaps I'll take more inputs from you now since you have already studied this. So we'll define those 3 or 4 methods of this search tree. So now we have reduced the problem of finding the goal state as a search tree problem and creating the search tree on a graph. And these methods that you are talking about will be applied here. So we'll just see how they can be utilized and perhaps in some way revise what you have already studied. All right then. Thank you for being here.
So for the searching purpose, we are going to use, I think, DFS and BFS sort of things.
Yeah, so that we have not, in our class, we have not talked about them yet, but these are the possibilities that we have. And then we'll see that which of these guarantees that you will reach a solution and what is the trade-off, what is the advantage, and combinations of these. So perhaps you have already studied them, so there will be some sort of repetition. So it will give you an opportunity to revise and perhaps contribute to this class. All right then, thank you for today. I'll see you on Saturday.
Thank you, sir.